For centuries we gazed at the night sky and saw order, a universe of Newtonian precision. Space was a vast unchanging stage, time a universal river flowing at the same rate for everyone. Planets moved in predictable orbits, stars were fixed, and every movement could be calculated if you knew the rules. This classical view painted space as a passive arena, like a giant empty warehouse, just there, inert and absolute. But as our tools improved, cracks appeared in this tidy picture. Mercury's orbit, for example, wobbled in ways Newton's laws couldn't explain. Tiny discrepancies hinted at a coming revolution. Einstein's general relativity showed space wasn't rigid, but a flexible fabric, warped by mass and energy. Yet, an even stranger revolution was brewing in the realm of the very small. The universe, it turned out, was not a predictable clockwork machine up close. Instead, it was a place of uncertainty and paradox. The smooth reality of everyday life dissolved into a choppy, probabilistic landscape at the quantum level. This new physics didn't just add a footnote, it forced us to redraw the very map of reality. Space was no longer a static backdrop, but something far more mysterious. And so began our journey into the quantum cosmos. The quantum revolution began with a radical idea. Energy comes in tiny discrete packets called quanta. Imagine climbing a staircase instead of a ramp. You can only stand on the steps, never in between. This quantization shattered the old continuous view of reality. Then came Heisenberg's uncertainty principle. You can't know everything about a particle at once. The more precisely you measure position, the less you know about momentum, and vice versa. This isn't a flaw in our tools, it's a fundamental feature of the universe. Quantum mechanics describes the world in probabilities, not certainties. An electron doesn't have a definite location until you measure it. Before that, it exists in a superposition of possibilities. Its wave function is a map of probabilities, like a weather forecast for where a storm might hit. The act of measurement collapses this cloud of possibilities into a single outcome. The universe is no longer a deterministic machine, but a cosmic casino governed by chance. Even Einstein objected, but experiments confirmed at the quantum level reality is a game of dice. This new set of rules would transform our understanding of space itself. The quantum world is not just strange, it's fundamentally unpredictable. And it's this unpredictability that lies at the heart of modern physics. The rules had changed, and so had our picture of the universe. In quantum physics, reality's building blocks lead a double life, sometimes particle, sometimes wave. This wave-particle duality means an electron can act like a wave passing through two slits at once, or like a particle, depending on how you observe it. Observation changes everything. The act of measuring forces the electron to pick a side. In the quantum world, particles are not solid dots but smeared-out probability waves. Their location isn't a fact until measured. The universe is a sea of overlapping probability waves, not a collection of billiard balls. The act of observation links the observer and the observed in a way classical physics never imagined. Space is not just a container, it's intimately involved in the existence of things. The wave function of a particle unfolds within space, defining its properties. Reality is a shimmering, uncertain landscape where particles are just concentrated ripples. The solid ground beneath our feet is an illusion, a fleeting moment of quantum certainty. Our perception of space and matter had to be completely reimagined. The quantum world had rewritten the rules of the cosmic stage. For most of history, empty space meant nothing, a perfect void. But quantum mechanics revealed a seething sea of activity beneath the surface. According to quantum field theory, empty space is a bubbling quantum foam, where virtual particles constantly pop in and out of existence. These fluctuations borrow energy from the vacuum, then vanish almost instantly. The Casimir effect proves this quantum foam is real. Two metal plates in a vacuum are pushed together by the pressure of virtual particles. The vacuum isn't empty, it's alive with energy. This vacuum energy, or dark energy, may explain why the universe's expansion is accelerating. Nothingness, it turns out, is a powerful something. The fabric of space contains an inherent repulsive energy pushing galaxies apart. The emptiness of space is one of the most powerful forces in the cosmos. Our old idea of a void was shattered. Even nothing is full of surprises. Quantum entanglement is perhaps the strangest idea of all. Two particles become linked so that measuring one instantly affects the other, no matter the distance. Einstein called it spooky action at a distance. There's no signal sent, just instant connection. Entanglement challenges our notion of locality. Space doesn't separate entangled particles. They remain part of a single unified system, even across the universe. Some physicists now wonder if space itself is an emergent property, built from networks of entanglement. The more entangled 2 points are, the closer they are in this deeper reality. Space may not be fundamental, but a byproduct of quantum connections. Entanglement forces us to rethink what space really is. Black holes are where the laws of physics collide. Einstein's relativity says nothing escapes a black hole, but quantum mechanics whispers otherwise. Stephen Hawking showed that black holes emit faint radiation, Hawking radiation, thanks to quantum effects at the event horizon. Virtual particles appear at the edge, one falls in, the other escapes, making the black hole slowly evaporate. This suggests black holes might not destroy information after all. The debate rages. Is information lost or somehow encoded in the radiation? Black holes are cosmic laboratories where space is stretched to its limit. Understanding them requires a new theory, quantum gravity, to unite relativity and quantum mechanics. The secrets of black holes are clues to the true nature of space, time, and information. We're only beginning to piece together this cosmic puzzle. The edge of a black hole may hold the key to the universe's deepest mysteries. We began with a clockwork universe, but the quantum revolution changed everything. Space is no longer a passive stage, but a dynamic, energetic player in the cosmic drama. The emptiness of space is alive, particles are also waves, and the universe is woven together by entanglement. Quantum physics lets us probe the most extreme environments, from the Big Bang to black holes. It's transformed cosmology from a descriptive to a predictive science. Yet, the universe remains deeply mysterious. The more we learn, the more we realize how much we don't know. What is dark energy? Is space fundamental, or does it emerge from quantum information? Can we unite gravity and quantum mechanics into a single theory? Each discovery opens new doors, revealing more mysteries. Our journey from the clockwork cosmos to the quantum cosmos is a lesson in humility. The universe is stranger than we can imagine. And that's what makes the quest for knowledge so thrilling. The adventure is far from over, the cosmos is waiting.